Hello everyone, my name is Kazuki Nomoto, and I am a second-year master's student at Waseda University in Japan. Today, I will present on the feasibility of linking attack to Google Apple Exposure Notification Framework. This research is a collaboration of Waseda University, NTT, Ministry of Internal Affairs and Communications, Osaka University, National Institute of Information and Communication Technologies, and RIKEN Center for Advanced Intelligence Project. First, I provide a background of our research. Contact tracing is used worldwide to prevent the spread of COVID-19. Discrimination and prejudice against persons who are COVID-19 positive and healthcare workers is a social problem. People's privacy should not be threatened by contact tracing. I present an overview of this study. We targeted Google Apple's exposure notification, which is a representative implementation of digital contact tracing. We proposed and evaluated the face photo linking attack. This attack is to link a person's face photo to his or her COVID-19 infection status. We addressed three research questions. The first is a linking attack target the Google Apple Exposure Notification Framework feasible? The second is the attack scalable? The last is, what is the effective approach to mitigating the attack? I will present today along with the order of these research questions. First, I explain about close contact. A close contact is someone who was less than 1.8 meters away from an infected person for a cumulative total of 15 minutes or more over 24-hour period. A person in close contact with a positive person is likely infected with COVID-19 and should be isolated and PCR tested. Next, I explain contact tracing. Identification of close contact has traditionally been done manually. In COVID-19, a mechanism was established to automatically detect close contact using digital technology such as smartphone, QR codes, and Bluetooth. This mechanism is called digital contact tracing. The Google Apple Exposure Notification Framework is a representative implementation of digital contact tracing. This framework was developed by Google and Apple. It is installed as standard on Android and iOS. This is widely used in 38 countries. Exposure Notification Framework uses Bluetooth Low Energy to send and receive identifiers to each other. The framework installed on each smartphone sends its own identifier to the smartphone of others, as shown in this slide. The smartphone stores the identifier received from the other's smartphone. Next, I will explain how close contact detection works in the exposure notification framework. COVID-19 positive users upload their identifiers to the app server using the app functions. The app server distributes the uploaded positive identifier to all app users. The app compares the positive identifier with the identifiers it has received and stored from various people over Bluetooth Low Energy in the past. If the stored identifier and the positive identifier match, then close contact is detected. Based on these backgrounds and mechanisms, I will describe the attack procedures. I show the threat model. The attacker aims to automatically collect face photo of COVID-19 positives. Initially, the attacker links the identifier to the sender's face photo. For example, this sender transmitted the identifier 123. This switch transmitted the identifier CCC. The identifier of positive person are distributed by key servers. The attacker gets the positive person's identifier. The attacker compares the positive person's identifier with the result of one previous step to find the positive person's face photo. As a result of these steps, the attacker is able to obtain the positive face photos. In these attack procedures, linking in step 2 can be easily feasible with an implementation that follows the algorithm. The key point of this study is step 1. We use signal strength variations to link identifiers to the target. The attacker places a Bluetooth low-energy receiving antenna at a location where pedestrians walk. The attacker continues to receive identifiers transmitted by the smartphone. The figure on the right is an image graph of the relationship between time and the signal strength. It is assumed that the signal strength increases as the target approaches in front of the receiving antenna and decreases as it moves away. The attacker links the identifier to the sender by using signal strength variations. From here, we show the feasibility of linking attack on research question 1. I show the setup of the experiment. In the experiment, 2 cameras and a parabolic antenna connected to a Bluetooth low-energy receiver are set up as shown in this figure. Pedestrians walk in front of this setup. This graph shows the relationship between time and signal strength recorded in the experiment. The blue dotted line plots the time and signal strength of the received signal. The red dotted line is the time when the pedestrian reaches the front of the antenna. The blue star mark is the time when the signal strength is at its maximum. The result demonstrates that the timing when the signal strength of the target is at its maximum and the time when the target passes in front of the camera are very close. I show photos taken by the camera at the time of maximum signal strength. The target is captured in the center of the photos. This result means that the timing-based linking attack is feasible. In addition, this study evaluated the impact of smartphone models, distance between the receiving antenna and the pedestrian, and how the smartphone is held. I omit detailed results of the experiment in this presentation, but we found that the attack was lowest for these conditions. Next, we evaluate the scalability of the attack. In this study, we built a simulation of human flow and signal strength. We used the simulation to evaluate the attack success rate. The walking speed of individual pedestrians is given by the normal distribution. Pedestrians are assumed to arrive randomly according to the Poisson process. The signal strength received by the attacker's parabolic antenna is computed using Fourier's transmission equation. Fourier's transmission equation shows the relationship between antenna gain, signal strength, wavelength, and distance. In this presentation, I evaluate the attack success rates by focusing on the number of pedestrians per hour and the number of attack devices set up. I show the result of the simulation. This table shows the relationship between the number of pedestrians per hour, the number of attack devices set up, and the attack success rate. When the number of pedestrians per hour is 800 and the number of attack devices is 1, the attack success rate is 83%. When the number of pedestrians per hour is 5000 and the number of attack devices is 1, the attack success rate drops to 38%. This means that as a result of reduced distance between people, it has become more difficult to link identifiers to their senders. The attack success rate increased to 75% by increasing the number of attack devices placed to 3 and increasing the number of attack attempts. These results show that this attack has a high success rate of 83% in uncrowded spaces and a high success rate of 75% in crowded spaces by increasing the number of attack devices. Finally, we present countermeasures against this attack. We proposed and evaluated 2 effective countermeasures against the linking attack. Please refer to the paper for detail and evaluation of the countermeasures, since we omit them in the presentation due to time limitations. I show ethical considerations. We reported our findings and actionable countermeasures to Google and Apple, the developer of the framework. The attack is not caused by a specific application's vulnerability, but by the design of the digital contact tracing framework based on Bluetooth Low Energy. We believe that publishing this paper will provide insight and benefit broad stakeholders. I show a summary. We conducted a field experiment using a real equipment and a realistic simulation experiment that incorporate radio characteristics and a 3D model of a human being. The result demonstrated the linking attack is highly feasible and that an attacker can succeed with a probability of 75% against the high pedestrian traffic flow of 5,000 people per hour by installing a few attack devices. In addition, we proposed effective countermeasures. We hope that the findings of this study will contribute to the design of a digital contact tracing framework with improved privacy protections. Finally, we discuss future directions of research based on the findings of this study. This study shows that linking the transmitter to the content of the transmission can be easily feasible. This finding raises fundamental privacy concerns about the mechanisms that emit radio waves. For example, linking attack target Bluetooth and Wi-Fi communication can reveal the sender of the communication. While this is one example of de-anonymization using a linking attack, the linking attack raises concerns for numerous mechanisms that emit radio waves, not just digital contact tracing. We suggest appropriate evaluation and implementation of countermeasures for each of these mechanisms as a future direction. Thank you for listening.